Our guest speaker is Aman Chadha. He is the head of AWS Generative AI team. Aman manages the generative AI team of scientists and managers at AWS, focusing on pre-training and fine-tuning LLM and VLM models for a wide range of use cases. During his tenure at Amazon Alexa, he spearheaded query understanding and personalization, enhancing user interactions while maintaining safety and reliability. At Apple, as a part of the Machine Intelligence Neural Design or MIND team, he specialized in designing on-device multimodal AI models for applications including NLP, computer vision, and speech recognition. In parallel to his industrial role, Aman actively advises projects in academia focusing on diverse areas in generative AI. He has co-authored papers in leading conferences and journals, including ACL, EMNLP. He has outstanding paper awards at EMNLP 2023, AAAI, ACL, and etc. His work has been featured in media outlets such as the Washington Post, Nature, Wikipedia, New Scientist, etc. All right, Aman, the floor is yours.
Awesome. Thanks, Ra. By the way, I can't see you guys, just so you guys know, that is totally fine with me.
The problem, we have some technical
Okay.
here. So I'm just going to share the video, and whoever has questions, please come over here so we can see.
Perfect. All right. Well, great to connect, folks. Let's get started. So we're going to be talking about responsible AI today, and responsible AI is obviously a very broad umbrella term. There's a whole lot of different components to creating responsible end-to-end systems. So we're going to start off on the right, you'll see the agenda. So we're going to start off talking about why we need trustworthy or responsible AI. So we're going in, clockwise order, right? So we'll start off with why trustworthy AI first. Then we're going to talk about bias. And bias is a big part of what makes, AI, irresponsible. So, detecting and mitigating bias is obviously a big step in the journey to responsible AI. So we're going to talk about a couple of different methods. We're going to start off talking about some of the seminal work in this field, a couple of seminal papers that have really shaped up the field. And we're going to also talk about a recent paper that we published recently at AAAI earlier this year, AAAI 2025. Talking about how to debias these large language models by using few-shot learning. So that's going to be the agenda for bias detection and mitigation. And then we'll move over to hallucination detection and mitigation, which is yet another very relevant area to responsible and trustworthy AI. We're actually going to spend most of our time in this particular area. There's a lot of work, in this field. The momentum is pretty solid in terms of, how do you detect hallucination in not just large language models, but also, multimodal large language models like vision language models, for example. There's hallucinations of various types and forms, depending on which model you're utilizing and what the specific kind of model it is, the kind of modalities that it interacts with in particular. So we're going to talk about detection as well as a bunch of different mitigation techniques that have shaped up the field. And then further on, we'll move over to responsible AI agents. So agents, as you guys are likely aware, is obviously picking up a lot of momentum in the area. Agentic AI workflows are being deployed in the industry for all kinds of different use cases, be it customer support or coding, for example, is a very common use case with Cursor and Replit and Lovable. A lot of startup momentum in this area too. So while this is a budding area, there is some work done here in terms of shaping up architectures that ensure that we have the necessary checks and balances at different stages of the agentic AI pipeline. So that's going to be the next area that we'll talk about, responsible agents. And lastly, I will conclude today's talk around the 1 hour mark from now on to talk about various pointers that you guys can go over to get a deeper understanding of whatever we discussed today. So I've got a bunch of papers that you can go through, beyond what we are going to discuss today. So there's a list of papers as well as some primers that I've written on my blog online that help you understand some of these areas in a little more detail. So that is the agenda for today, folks. And with that, let's get started with why trustworthy AI. Oh, hold on. Let me see. I think there was some issue with the slides. Yeah. All right. Why trustworthy AI? So as we just touched upon, right, LLMs and intelligent agents are increasingly being deployed, whether it's academic research or real world workflows, for solving problems, in the industry. We're seeing momentum for some of these models being deployed. And, with that, the need for transparency and explainability couldn't, be more urgent, right? Because both of these aspects go hand in hand. You can't deploy these models, confidently unless you understand how to decode some of the decisions that they make, right? At least to some level or some degree. So we're seeing a lot of momentum in this area, the area of responsible AI. And if you talk about fields such as law, healthcare, and policy, which are all fields that are mission critical, right? In the sense that a decision that is made, in these fields with an LLM system that is deployed, it's essential to understand why the system came up with a particular decision, how the outputs were generated, and what kind of data influenced those results, right? So to be able to tease apart what led to that decision, and understand what the specific weightage of the inputs were as the model made a particular decision. I think a lot of that is absolutely core to creating a notion of understanding as far as these models are concerned. And this is exactly where trustworthy or responsible AI comes in, right? So there's, like I mentioned earlier, this is a broad umbrella term. There's a lot of different verticals or pillars within this area. So there's bias and fairness, which we're going to talk about. There's hallucination, detection and mitigation. And fact verification, by the way, is also a key area, and you can club that together with hallucination, because at the end of the day, we are looking to figure out, the output of the LLM, which specific aspects or claims that were made within the output are relevant and are true versus claims that can't be substantiated or supported with some data or knowledge base that you have, right? Could be even an internet search, for example, internet search over authentic web sources. So hallucination and fact verification in that sense go hand in hand. There's also responsible agents, which we talked about earlier, and there are other components to responsible AI as well. Beyond what we're going to be touching upon today, there's privacy preserving AI, for example. I worked on this back in my time at Apple, which has a strong on-device focus. And the idea is basically to come up with models that can run either on device or can run on the cloud, but in a way where we aren't sharing, customer data over to the cloud, right, as we run these models. So there's a whole lot of techniques within privacy preserving AI. And adversarial robustness is a big area in responsible or trustworthy AI as well. Whether it's jailbreaking or prompt injection, a lot of different techniques to be able to steer these models, and get them to a point where, none of the guardrails or alignment, that they went through during the post-training process are being followed, and they give you answers for questions or queries that are basically not supported by some of the guidelines that they were initially aligned to during the post-training process. So adversarial robustness is huge as well, and there's a lot of work being done there too. But today's talk is going to be focusing on the first three areas primarily. So we're going to be touching upon bias and fairness first. We're going to be talking about hallucination detection and mitigation, and then we'll touch upon responsible agents. Now let's look at a quick overview of these three areas one by one. So bias and fairness, the models are only as good as the data that they're trained on, right? So garbage in, garbage out is what we like to say. So, it's important to scrutinize the training data to understand what are some biased, what are some biases in various subpopulations within the training data. And when I say subpopulations, I mean dimensions such as, gender, religion, occupation, for example. and understanding, what are some of the biases, embedded within each of these subpopulations, which are eventually leading to unfair outcomes. Right. So this is a key part of what makes bias and fairness research happen in AI, developing this understanding. And at the end of the day, what we are seeking are equitable systems that, not only, go through continuous auditing, but there's, the data sets, like I mentioned earlier, the training data sets that they're trained on are diverse enough. And, some of the biases within each slice or dimension or subpopulation of the data set are understood and mitigated to some extent. And we'll touch upon some of these techniques that have been prevalent in the field, right from debiasing embeddings to debiasing the output of a generative model, like, some of these LLMs that are pretty common in the field right now. And lastly, there's also the idea of inclusive evaluation, right? So when we run evaluation for these models, whether offline evaluation with, metrics, a whole range of different metrics that we typically evaluate these models on, depending on what use case it is that they're serving, whether it's offline evaluation or even online evaluation with A/B testing and other forms. How do we ensure that these evaluation processes and methods are inclusive enough, right? That we're doing targeted evaluations for each of these subpopulations or each of these slices of the data set, sorted by various criteria. Like I said, gender, could be gender, could be religion, could be occupation. There's a whole bunch of different dimensions that we could slice and dice our test set on, and then ensure that for each slice, we have, the right representation. So, the idea is to make sure that the evaluation process itself is inclusive, because evaluation, in turn feeds, the next iteration of training, right? For the model, you understand what are certain areas where the model isn't doing well on, right? Where is it biased enough? So you can mitigate those biases in the next iteration. So that's the idea for bias and fairness. And then hallucination, the definition for hallucination is obviously factually incorrect, inaccurate outputs, right? And the idea is that, when you deploy a model in production, it poses a lot of risks, especially in critical applications, because detecting and reducing hallucinations is a big challenge. And because think of something like deep research, right, which is pretty popular right now. So if you run deep research from one of these vendors right now, how do you ensure that once you've got like tens of pages of output, right? How do you understand where there was a certain piece that was factually inaccurate, and that further snowballed into an argument within the output, right? And set up a bunch of different paragraphs, or came up with a narrative that led to a big amount of hallucination within the output, just because of the snowballing of hallucination that happened, because the model came up with a small piece that wasn't factually inaccurate, and that led to another, and eventually that process led to maybe half of the output being inaccurate, right? So detecting this kind of a needle in a haystack, where something is factually inaccurate, and that leads to a whole narrative around it, especially in a form like deep research, a long form output like deep research, is particularly challenging. And we've got a whole bunch of different ideas in the field in terms of detecting and mitigating hallucination. So we'll touch upon some of those ideas. Responsible agents, the idea obviously with agents is to, have, autonomy, right? Have, a large language model, get it access to tools so it can carry out action. But delineating where that, ethical boundary is, where it respects human intent, and is able to handle ambiguity and uncertainty responsibly, is obviously a big part of deploying some of these agents. So we'll touch upon some studies in that area as well. So these are the three pillars that we're going to cover for trustworthy AI. But like I mentioned earlier, there's a whole bunch of different pillars as well under the trustworthy AI or responsible AI umbrella term. All right. All right. With that, let's step into bias detection and mitigation. And by the way, if there's questions in line, Ra, feel free to pause me at any point in time. We're now getting into the core content of today's talk. So, I anticipate that there could be questions, but I'm happy to take them at the end as well, whatever works for the audience. But this is our first filler, bias detection and mitigation. So this is a quick overview. What are some of the key studies or papers in this area that have shaped up the field? And we're going to touch upon two key papers, which are cited here on the slide. The first two papers are going to be papers from that have shaped up the field. The first one actually came, prior to the era of transformers back in 2016, Europe's 2016. This was a very well-cited paper. 4,000 or so citations, has really shaped up the field of bias detection and mitigation. And we'll delve deeper into each of them, but this is just a quick overview. So we're going to talk about the first one, and the second one actually proposed Vino bias, which is a very common data set in the field of bias detection mitigation. So that we're going to touch upon that as well. And the third paper that we're going to cover is based on few-shot learning, debiasing using few-shot learning, which was a paper that we published earlier this year at AAAI 2025. So we're going to touch upon how we went about that process as well. So this is how we're going to structure the next couple of slides. And before we get there, let's talk about how do you define bias, right? And bias is a pretty overloaded term in AI right now, but the general idea is that if there's any systematic deviation that unfairly favors a particular group, for example, gender, could be religion, occupation, and this could be typically rooted in any sort of inequality, right? Could be historical, societal, or data driven. So if we see any kind of unfair favor happening for a particular gender, a particular group, for example, gender, occupation, religion, that typically is termed as bias, right? And the thing with today's models is that we've got models that are embedding models, and we've got models that are generative models, right? Or the decoder models, the LLMs or multimodal LLMs. Now, bias can manifest in both sorts of these model architectures. You could have bias along the embeddings, in certain dimensions of the embeddings that these embeddings models generate, for example, BERT. And the first paper that I was talking about earlier, Man is to Computer Programmer as Woman is to Homemaker, this was a landmark paper in the field, which basically dissected the idea of bias for these embeddings along the gender dimension. So they were focused primarily on the gender dimension and showed that with embeddings that were at that point, like I said, this was prior to the transformer architecture back in 2016. Transformers came in 2017. So the paper mostly focused on word-to-vec embeddings at that point, and showed that there was a propensity for these embeddings to be biased to, as far as genders are concerned. There was definitely inequality that was being seen. So this is a classical example of bias, for embedding models. And then, we had Vino bias that came out a couple of years later, and this is again a standard data set in the field to detect and mitigate bias. And we'll talk about this in a little more detail in an upcoming slide. But then looking at the data-driven debiasing approaches, there's a whole bunch of different ideas in terms of debiasing embeddings or even generative output from a model like Llama, for example, or ChatGPT, right? So you can do a lot of post-processing on the output and have a model at that accepts the output of a prior decoder model that looks for certain patterns of bias and then debiases the output as well. So we've got two sets of different options depending on what type of model architecture you're dealing with. So if it's embedding models, the first paper that we talked about offers some insight in that regard. So we'll touch upon that as well. But if it's a generative model, we experimented with few-shot learning in our paper. And that helped bring down the amount of bias, the magnitude of bias in the output as well. So there's different approaches depending on what type of model architecture it is that you're dealing with, whether it's an encoder or a decoder. And then lastly, there are some general techniques as well in the field in terms of debiasing. You can look at gender swapping, for example, and come up with an augmented version of the data set, which essentially debiases some of the inherent biases in the model by ensuring that the data set is more holistic or well-rounded and looks at both genders similarly, right? And obviously, gender is, placeholder. In this case, you could apply the same idea to, religion bias or occupation bias or any other dimension of bias. But we'll touch upon that as well. But the key idea here is, as we carry out some of these techniques, we want to make sure that we don't degrade the ability of these models, right? So we do, and you'll see that in the upcoming slides where as we talk about each of these methods, we'll see that during evaluation, these methods ensure that we aren't losing our performance on general purpose tasks. So they do a lot of regression analysis, for example, to understand that at the level of performance that we were seeing pre-debiasing versus post-debiasing. So we'll look at some of those patterns as well. But let's get started and delve into the first paper that we touched upon in the prior slide. So this paper, like I mentioned, predates transformers even, and this was a landmark paper in the field. And they took word-to-vec embeddings, which are trained on Google News data, and analyzed the biases within the data. And on the right, you'll see that associated with, they saw a whole bunch of different occupations, which were very different compared to what they saw with, he. So you'll see two sets of very different occupation and the kind of associations that the word-to-vec embeddings learned, as it was trained on Google News data. Right now, these embeddings, obviously, based on their findings, show bias, right? But the problem is that as these embeddings are used in a system downstream, which utilizes these embeddings to say, perform classification, for example, you're going to amplify the stereotypes even further. So in this case, they saw that man was more closely related to computer programmer versus a woman was more closely related to homemaker, which was a classical sign of bias in the embeddings. And whether it's a search engine, for example, or even resume parsing for ATS systems online, the problem is that if there's a bias in these embeddings, it's going to unfairly favor certain associated terms with a specific gender, right? And this is going to amplify or exacerbate societal inequalities. So this was the finding that they had. And what they did was they detected a low dimensional gender subspace within the embeddings, which was basically they found that this subspace was responsible for introducing some of that bias, and they carried out hard and soft debiasing techniques to be able to neutralize some of these associations. And like I said earlier, right, as we debias, the key point here to note is that we want to make sure that we don't lose performance of these embeddings on other tasks, right? So they did, as they debias, they also ensured that they weren't harming neutral relationships between different kinds of terms. And the end result was essentially that they saw some of the stereotypical analogies going down from 19% to 6%, which is a huge reduction, and while at the same time maintain performance on other standard benchmarks. So this was a key paper, like I said, in the field, cited about 4,000 or so times, and I've linked the paper down there. I've cited it, so feel free to take a look. But this was kind of an early paper that really created waves in the field and made us understand that there's a strong influence of bias in some of these embeddings, especially if they're trained on data that is just obtained off of the web. In this case, Google News data, which isn't curated as well. There are some of the techniques that they propose for debiasing models are still, prevalently used in different forms and variants, but a key paper in this field for sure. Now, next up, we've got We Know Bias, which is again a landmark paper in the area of bias, cited a couple of thousand times. And The idea was that this paper looked at gender bias similar to, the last paper. So that was their scope. But they looked at gender bias in the context of co-reference resolution. And if you see the figure on the right from the paper, you'll see that, there's different occupations, the physician, secretary, for example, and they're making core references or linking with some of the core references. And by the way, a core reference in NLP is essentially, an indirect reference to a particular entity, right? So in this case, you've got he and she, right? In the two lines that you see for both type 1 and type 2. And they're basically trying to figure out what the core reference is when, and what the model refers to when it comes across a he within a sentence that has two different forms of occupations, like in this case, a physician and a secretary versus a she, right? So this is what they primarily focused on, the problem of co-reference resolution, which, by the way, lends itself very well to bias detection because, if you make a model connect the dots between, an indirect reference such as a he or she to, an entity within a particular sentence or a corpus, that tells us what the propensity of the model is to link particular gender in this case with a particular occupation, right? So this is what the paper mostly focused on, and they introduced the Vino bias benchmark, which basically showed that co-reference systems linked, some of these gendered pronouns like, he and she to stereotypical occupations, right? And there was a big disparity there as well. And the why or the idea behind the paper was to check, or to identify, what magnitude of harmful stereotypes were we perpetuating in AI applications, right? Um, and the way they tried to address some of these problems in the paper was, like I mentioned earlier, gender swap data augmentation is a very common strategy. And this is exactly what they deployed, right? So they debiased word embeddings by training on data that was augmented enough to be well-rounded and holistic, where it had, both, the good representation across different genders in this case, because they were focused on gender bias. But the idea was to make sure that the data had enough of representation for all the different dimensions. And, the gender is again a placeholder here, but you could carry out a very similar study for a whole bunch of different bias dimensions as well. But what they saw was doing this, gender swap data augmentation neutralized some of these learned gender association that the model had, while at the same time ensuring that we did not lose predictive power on other tasks, right? Um, and the end result that the paper showed us was basically the disparity here in terms of these gender associations dropped to 1.1 points on Vino bias, which was significant compared to what they saw earlier with the baseline. While at the same time ensuring that they saw, strong performance on other kinds of, downstream data or downstream tasks, and they use onto notes as a data set to check for performance before debiasing and after debiasing. And essentially the key takeaway here was that with some of these interventions you could reduce bias significantly without introducing a major trade-off. And this served as a blueprint for a lot of the downstream systems that came about. But again, a pretty well cited and well referenced paper in the field. And Bino bias is again a benchmark that we utilize very commonly in academic research as we come up with new techniques and to benchmark our technique against a whole bunch of different proposals. Bino bias is definitely one of the most prevalent benchmarks. All right, and this brings us to the last study for bias detection and mitigation, and this was a work that we published earlier this year, which was mostly focused on, today's LLM models, right? How do we utilize a standard data set out there? How do we reference that to be able to bring down the magnitude and level of bias, right? So in this case, the standard data set that we used was data from the US Bureau of Labor Statistics. NBLS is, how it's commonly called. And we came up with a prompt. So this was a prompting based technique, by the way. So we weren't changing the model's weights at all. We weren't fine tuning it, unlike some of the other techniques that we saw. So this was a different flavor.
Question.
Alexa, Stop. Sorry, I triggered my Alexa device. Um, but the idea was a little different compared to the other techniques, right? We were focused on mostly crafting a prompt that had a few short examples within it that which gave a signal to the model to be able to debias its outputs, right? So we compared the outputs before and after some of these few short examples, and you could clearly see that bias that was present before, including some of these examples, and specifically telling the model to identify certain types of bias within these examples that were offered to it, and be able to mitigate them as it generates its final output. There was definitely a big variation, before after variation that we saw. So looking into the key idea, like I said, there's a whole lot of different sectors, that utilize some of these models to make critical decisions. And without some of this correction, obviously going to perpetuate, the stereotypes that we see around gender, ethnicity, occupations, and a whole bunch of different dimensions. So what we did was we looked at, we actually swept the value of k being the number of examples that we added to the prompt. So we went from a couple of examples, to examples or so, to 32 examples within the prompt. And there was also a method in terms of how we chose these examples. So that was also proposed in the paper. And that, the models were diverse enough to give the main model, the LLM, a signal in terms of what to look for as far as biases are concerned, and what kind of strategies to use to debias its own output. So the end result that we saw was that with 32 examples, we saw a significant drop in bias scores, up to 92%, with, for example, with GPT Neo, where the bias score decreased from 1.07 to 0.09. So a significant reduction. And all of these examples were basically chosen in line with with the data that we had from the US Bureau of Labor Statistics, to ensure that we had an authoritative enough data set and that we could follow it to be able to debias some of the outputs. So this was a scalable, low cost way. Like I said, purely focused on prompting. So we didn't have to carry out any expensive, continued pre-training, for example, with a base model, off the shelf base model, or fine tuning, full fine tuning, or parameter efficient fine tuning. We did not have to modify the weights at all, but with just enough demonstrations within the prompt, we were able to, give enough signal to the model to be able to debias its output without any kind of retraining. So that was the idea behind this paper, and I've cited it down there, and I've got a whole slide with a whole bunch of different references, and this included there as well. So if you'd like to take a deeper look and understand, certain nuances about this study, I'd encourage taking a look at the paper. All right, and with that, let's get into the core part of the talk today, and I've got a whole bunch of techniques here to cover. So we've got a whole lot of slides for hallucination detection as well as mitigation. So this is a quick overview slide that defines hallucination first, and then we're going to talk about some of the key techniques in the field that have steered the field over time, over the past several years, and the kinds of different strategies that these techniques use to be able to detect hallucinations. There's a whole range of different methods, and we'll touch upon 3 of the most popular techniques. But in terms of, how do you define hallucination? It is essentially output that the model is confident about, but is factually incorrect, or output that is just pure fabricated. Like I said earlier, right, with deep research, for example, it's a new area or product in terms of how we're going to be utilizing some of these models, and has a lot of merits to it. But hallucination in a case like this can really undermine user trust and real world applicability. With short form output, like us interacting with a model like ChatGPT, for example, it's typically easier to figure out if there's anything off with the output, by looking at sources and reviewing some of that output manually, even, or even doing post-processing of the output and employing some of these techniques, as we'll talk about. But with long form output, it becomes much more challenging, right? And hallucinations also have a tendency to snowball. So one particular hallucination might lead to another, and so on and so forth. And that leads to, a whole lot of, it's kind of a wild goose chase, right? To be able to figure out what is true and what is not. So there are a bunch of challenges in this area still, and we're not even remotely close to solving some of these issues. But there are a bunch of techniques. Self-check GPT is one of them, which basically detects hallucinations by sampling the output of the model multiple times. So it just varies the temperature hyperparameter to be able to get multiple different outputs of the model to the same question or the same query that was offered to it. And essentially, what we do is we just look to identify any contradictions, right? And what was a fraction of divergences that we saw across all of these samples that were generated at the output? And it's a black box method, right? So we don't get into the core model or inspect the activations within certain layers, for example, or look at probability values. We're basically relying on just sampling the output of the model, rerunning it multiple times to be able to generate models with varying temperatures, and just figuring out what the proportion of match versus mismatch is. And we're not even relying on external databases or any sort of external knowledge base for this particular technique. So that's self-check GPT. And I've got a slide for each of them where I'll be going into more detail and give you guys a visual description of these techniques as well. With leveraging some of the diagrams in each of these papers and also giving you a more in-depth idea. So we'll get into that as well. But fact score is yet another technique which starts off by breaking long form output into various individually standalone atomic facts. And then what we do is we verify each fact individually, right? So it's a much more fine-grained technique compared to self-check GPT, and much more rigorous because it gives you a proportion number, right? A score at the end of the day in terms of how many atomic facts matched what we had in our external knowledge base versus cases where there were a mismatch. So that becomes your score at the end of the day. And again, this technique is different compared to subject GPT in various aspects. Like I said, where it's more fine-grained, but there's also the reliance on an external knowledge source. Could be a database, could be a knowledge graph, even could be an internet search. So there's you will need a reference to compare your individual atomic facts against. So that's fact score. GEVAL is yet another technique which basically uses LLMs to self-evaluate the generated text via structured prompts. So we're going to talk about that as well, and it utilizes chain of thought reasoning, and eventually the end product of GEVAL is a distribution with different values going from 1 to 5, similar to Likert scale, and it comes up with probability values for each of the different ratings within 1 to 5, so 1, 2, 3, 4, 5. And then it comes with a weighted sum at the end of the day, and that becomes the GEVAL score. And we'll get into more detail on the GEVAL slide. But these are three common or prevalent techniques in the field, so we'll touch upon these as well. And like I mentioned earlier, fact verification goes hand in hand with hallucination detection. So a lot of these techniques are pretty interchangeable depending on what you're looking to verify and confirm. All right. Let me see. Yes. Now, self-check GPT, and again, I've structured all of my slides into the what, why, and how, and so what, right? So we're going to cover the motivation behind the idea first, the what and the why becomes the idea itself, and the how is going to tell you more about the implementation detail, and the so what is going to talk about the results. So the what here is essentially with self-check GPT, like I mentioned earlier, we wanted a zero resource or a black box approach which essentially does not look at the model's internals at all, but is able to give us some signal of hallucination. And the way they did that was using, sampling-based methods by varying the temperature, which is a hyperparameter that we typically utilize during sampling. And this lets us evaluate the consistency of generated responses and without relying on any external knowledge source. So that was self-check GPT at a top level. And the idea was that obviously the end goal was to enhance reliability and trustworthiness of these models. In the event that you did not have any references or external knowledge bases to rely on, the idea was that self-check GPT was, a standalone implementation by just having the model and being able to sample from it multiple times without needing to get into the model architecture. So if you say, for example, with ChatGPT or, closed source or closed weights models, where you did not have access to the model's internals, this is a great idea to implement. In fact, you can implement this with ChatGPT too. But essentially, it's a type of a black box method for that reason. And on the right, you'll see that, with a specific input or the input prompt that is offered to the model, we generate a whole bunch of different stochastically generated responses, each with a different value of temperature. And you could actually utilize a whole bunch of different techniques too by, for example, sampling with top P sampling or top K sampling instead of just this regular greedy decoding, which is selecting the probability of the highest probable token by doing an argmax on the maximum probability, right? Which is typically how we sample from these LLM models, but you could look at other sampling methods even to generate these stochastically generated responses instead of just varying the temperature. So many different ways to generate multiple different outputs from the model. And then what we do is we then pass on these outputs to another LLM call, and this could actually be the same LLM, but this is another call which basically looks to compare all of these different outputs and ensures that there are outputs that overlap with each other, and that becomes your eventual self-check GPT score to understand what was a fraction of consistent outputs that we received from a particular LLM. So that's the idea behind self-check GPT. And in terms of the results that we saw, the obviously, like I mentioned earlier, the idea was that the LLM to check if the LLM had enough knowledge about a particular concept that you were discussing as part of the prompt, and that it was able to generate consistent outputs, right? But if in the case that the model's hallucinating and if it's a hallucinated fact at the output, the idea was that stochastically sampled responses using, like I said, either varying temperature or the kind of token sampling method that you used, you would see that, a divergence in the output, right? And in fact, even contradictions. So the idea was to look for some of these instances. And then if you look at the results that they reported, right, the last section within the table are the self-check GPT results, and you'll see that, given, a prompt, we were able to, across different kinds of, metrics, area under the curve with precision recall, which is the sentence level set of first three columns. And even at the passage level, a correlation coefficient, including they looked at Pearson and Spearman, the standard correlation coefficient. We saw that all across the board, relative to GPT-3, Llama 30 billion, we saw superior performance all across. So this method really helped in terms of detecting hallucination. But the obvious challenge here is obviously invoking the LLM multiple times for each output that it generates, and then having to again invoke the LLM to compare all of these outputs and come up with the final score. So that was the downside to this method, but it did help bring down the magnitude of hallucination in a whole bunch of different cases. Now, fact score, the second technique that we're going to be discussing for hallucination detection, the idea behind fact score is to measure the factual accuracy of generated text. And step one in terms of, to generate the fact score is to break down the generated text into, various different atomic standalone facts, and then compare those facts with, a knowledge base. And like you could implement a whole bunch of different techniques to power these knowledge bases, right from, another vector database, or it could be, a relational database for that matter. It could be an internet search, could be a knowledge graph. And, looking at this reference, fact score basically provides a fine-grained evaluation compared to a binary judgment, which is what self-check GPT initially focused on. So the idea is that this is a more precise assessment method, and ultimately offers a much more accurate and detailed measure of factual precision. So on the right, you'll see that we offered an input, and I believe they looked at the data set that they experimented on was mostly author biographies, where, you got a lot of different factual content. And one such line from the biography data set basically, split the entire, set of sentences into various different atomic facts. That was step one. And then it compared all of these facts with Wikipedia to come up with, a fact score, right? So that was the idea behind a fact score. And, just to go over the algorithm formally, they come up with atomic facts, which are essentially defined as short sentences with a single piece of standalone information, right? And yeah, the second bullet point here mentions what we just discussed. Biographies were utilized for evaluation and are typically key in a lot of these scenarios, especially you'll see that with a lot of hallucination techniques, because they generally contain a lot of, different pieces of information within a single sentence, right? Talking about the main person, around which the biography is based. So the idea was that they applied an automated estimator to be able to, break text into atomic facts, which was, an LLM call, and they then validated that with an authoritative knowledge source, right? Now they experimented with Instruct GPT, which was GPT aligned with preference optimization back in the day, Chat GPT as well, and Perplexity AI. So they looked at a couple of different options. And these are some of the results that they saw. So if you look at the legend here, they had a lot of different variants to their experiments, right? So they had a no context version, for example, where they just fed the input sentence to the LLM's prompt without including any additional details. The other option was to do a retrieval that gets passed on to the LLM. So that's a retrieval right arrow LM entry that you see in the table, where similar to how we do RAG right now, they utilize a passage retrieval system, and I believe they utilize the T5 model to be able to find supporting evidence from an external knowledge source. And in this case, most of their evaluation involved Wikipedia. And they retrieved relevant information within the prompt and had the model verify against that. And the other variant, the last variant that they used, was also adding atomic facts and their labels, within the prompt, where they basically had an idea of whether a fact is true or false after retrieving. So these were the three key variants that they utilized across a whole bunch of different models: Instruct GPT, Chat GPT, as well as Perplexity AI. And as you can see from the table, for all of these different variants, they saw significant performance, especially looking at the last particular configuration that they had, which involved retrieval as well as atomic facts. So this was a key technique in the field, again proposed, a couple of years ago in 2023, which really shaped up how and this actually led to, good impact on the field in terms of RAG as well, because retrieval is a key part of RAG, and retrieval helps in RAG helps in hallucination too, and we're going to discuss RAG too in an upcoming slide. But this gave us some of that early signal in terms of the fact that you could retrieve relevant information into an LLM's prompt, just like we do in RAG. And the model can then use that as a reference to bring down its level of hallucination. Now, GVAL is the last hallucination detection technique that we have, which relied on framework, which utilized chain of thought and form filling. Form filling is another word for structured outputs. And the idea was that it would come up with a form where the model can essentially fill against the particular evaluation criteria that GVAL uses as part of its prompt. And we'll get into more detail in the next slide. But the idea was that it would evaluate the input prompt based on various different evaluation criteria and fill in an output form, which would then let us have a distribution of scores from 1 to 5, similar to a Likert scale, as you can see in the figure on the right from the paper. So you'll see for each of the 1 to 5 integer outputs, we would sample the probability of that particular token, in this case, the token being, the output score going from 1 to 5. And then we would come up with a weighted sum of each of these different tokens, and that would be your eventual GWAL score. And this essentially gave us an idea of, how, relevant or how reliable the particular output is, because evaluation criteria were mostly focused on along reliability and judging if the particular, input prompt that was offered to it was reliable enough along various different criteria. And the key idea or the key takeaway here was that compared to metrics such as Blue and Rouge, which are great when there is, a lexical overlap with a reference that exists. In this case, all you need is, a model that is prompted well with certain criteria, and then it judges the particular input that you have for hallucination, along the criteria that are defined, and comes up with, a filled form at the output, which eventually gives us, a 1 to 5 weight distribution, and then we take the weighted sum of that to come up with the final GWAL score. Now, the sample prompt that they used here, just looking at factual consistency, theoretically you could apply the same framework for a whole lot of different kinds of evaluation as well. But their focus was factual consistency, which is closely related to hallucination. So the prompt on the right in the figure, you'll see that they asked the question: is the summary untruthful or misleading? Which essentially formed the core of the evaluation pipeline, right, for the model. And they use GPT-4, I believe, for running these evaluations. So the idea was that given this particular prompt and some source text or input text within the prompt, which we wanted to evaluate hallucination for, the model would generate a chain of thought outlining detailed evaluation steps, and then it would utilize the chain of thought to fill in a form which basically contain various different criteria for the model to judge the output against, or based on the chain of thought prompt, a chain of thought output. And that led to the final score, which was, like I mentioned earlier, probability weighted summation, right? So that was the final GWAL score. And the end result of this pipeline or this technique was that GWAL with GPT-4 achieved a strong Spearman correlation coefficient of 0.514 with human judgment. So the paper also looked at judging all of these outputs with humans, and then established that there was definitely an overlap between what GWAL came up with as a score versus humans, and it outperformed a lot of the previous methods. And this helped detect some of the hallucination, or even, like I said, same technique can be used for bias as well. And GWAL is actually a technique that is commonly used as well, even to date. So very popular technique in the field. Now, this is a list of some of the papers that we discussed, and there's a couple of more papers here. In the interest of time, I didn't add those, but the last two papers are not what we covered, but very relevant to the field of hallucination detection. So feel free to take a look. And I've got a much longer list toward the end of the presentation as well, and we can share this offline. So don't worry about taking notes, but a lot of different techniques, but these are some of the most popular in the field. Now, hallucination mitigation is obviously closely related to hallucination detection, but the focus here is to be able to either bring down hallucination generally, like for example, in the output of a model, reduce the propensity of the model to hallucinate, which is what RAG does by grounding the model in relevant corpora, right? And this could be done, via an external knowledge base. The idea behind RAG is to obviously reduce reliance on its core internal parametric memory, right? Where it has access to a knowledge base, and we retrieve relevant items from it. So that leads to a reduction in hallucination, right? There's a couple of other techniques as well. For example, is a popular technique too, and is purely prompting based. So we don't do any retrieval, unlike RAG. We're not fine-tuning the model at all. We're just having the model revise, come up with a revision plan, and be able to revise based on some of the facts that it has generated. And that leads to a reduction in hallucination. And there's also yet another class of techniques that look at, monitoring the confidence probability or confidence score that the models generate for each token. And based on those scores, in real time, it figures out where there could be lower confidence generations and looks at fixing hallucinations during generation in real time. So Stitch in Time Saves Nine is a common paper that implements such a technique of active detection by monitoring for low confidence outputs. And in the coming slides, we're going to get into each of these three in detail. So RAG is probably the most common technique to reduce hallucination, deployed, very prevalently in the industry in particular. And the idea is, very simple, right? The idea is that, we integrate a component, along with the main model, the main LLM of the decoder. You got a component here that retrieves relevant information from a backend knowledge base and then sends it back to the model, right? And this particular retriever can essentially be either a neural retriever, could be, neural retriever being, for example, like BERT, for example, or sentence BERT. A lot of different variants. We've got modern BERT now that came out a couple of months ago. So you could theoretically use any embedding model here, dense embedding model, but you could also couple that with a lexical, match, right, by looking at lexical embeddings, the more traditional sparse embeddings like, TF-IDF, BM25, Word2Vec, FastX, Glove, a lot of different options. And you could combine both of these lexical as well as semantic or dense embeddings via, say, a technique like reciprocal rank fusion, for example. And then essentially this gives the model access to relevant text within the corpora that has a lexical match as well as a semantic match. And all of that can be fed back into the prompt, depending on how many entries you can have in the prompt, right? Which is a function of the context window of the prompt, for example, or the amount of cost budget that you have to run these models, right? Because this will lead to more input tokens. But essentially, the idea is, fair and square. Get relevant information, feed it into the prompt, and that really helps ground the model, right? And this, as the paper showed, leads to a reduction in hallucination. So this is the idea behind RAG and how they accomplished RAG. And the original paper actually looked at a lot of different variants, to RAG. For example, they use dense passage retriever DPR, which retrieves with a dense embedding, which is very commonly seen right now in RAG implementations that we have in the field. And this enables a model to retrieve relevant documents. They also had a fusion in decoder FID variant to RAG, which was an end-to-end system which retrieves documents, encodes them, and combines all of these outputs before you start with the decoding process. Right, so this let the model attend to multiple different documents simultaneously. So this was a little bit of a different flavor compared to just vanilla RAG. And the eventual results that we saw here were pretty significant in terms of the reduction of hallucination. They looked at Wizard of Wikipedia and the document grounded conversation data set from CMU. And hallucination rates dropped by over 60% on some of these data sets. And they looked at both in distribution as well as OOD out of distribution data. And the model displayed significantly better output for both in distribution and out of distribution, 70% for in distribution and 85% for out of distribution. So this is a key technique in the field. And in terms of hallucination mitigation, this is typically the number one on the list for people to experiment with. I've got a bunch more slides, a bunch more techniques. I have to get into agents as well. So I'm going to try to expedite things. But I want to make sure we have some time for questions at the end as well. But yeah, next paper is a Stitch in Time Saves Nine, which utilizes a very different idea compared to what we saw earlier with RAG. The idea is to monitor the generation process of the model. So as you'll see on the right, as the model is generating data, it looks at identifying key concepts. And this is very similar to the idea of atomic facts that we saw earlier with fact score. And for each of these key concepts, it figures out what the level of uncertainty of the model is. This is based on the probability scores that are generated for each token. But once it understands that, it comes up with a validation plan, right? Where it basically creates a whole bunch of different validation questions and finds relevant knowledge from an external, knowledge base, and then answers those validation questions by comparing the key concept or that atomic fact versus what the external knowledge base says. And based on this answer, it then reruns the entire pipeline to be able to fix the hallucinated sentence. So that is the idea behind a stitch in time saves nine. And you can run this technique real time as the model is generating its output. So it's actively looking to detect and mitigate hallucinations. But it has both a detection as well as a mitigation component to it, which is, if you think about it, RAG is not explicitly looking to detect hallucinations at all. It is just looking to generally ground the model and mitigate hallucinations. But this particular technique does explicit detection and then subsequent mitigation of hallucination. Quick preview of results from this technique. So you'll see that, as far as mitigation of hallucination is concerned, we saw a significant reduction by using the active detection and mitigation technique, where the percentage of hallucination went from 47.5% to 14.5%, by deploying this technique. And this was experimenting with GPT 3.5. All right. Chain of verification. Again, this is yet another technique, but follows a very different strategy. And I wanted to make sure you guys have enough diversity across all of these techniques. So you'll notice that each technique uses a very different method. So chain of verification is mostly based on prompting. It does not involve any form of retrieval. Like RAG, it does not involve any form of looking at tokens in real time and active detection method that we looked at in the prior slides. But chain of verification, essentially, if you look at the diagram on the right from the paper, given a query, what it does is it comes up with a set of responses, baseline responses for that particular query, and then it comes up with a verification plan. Right. This particular part is similar to what active detection and mitigation does on the prior slide, where it comes up with various questions that help it isolate the individual facts, the atomic facts within the query, and then it executes this verification based on knowledge that it has either gathered externally or knowledge that it was prompted with. Right. So it looks at a reference and then executes a verification, and then finally, having all of this, accounted for, it comes up with the final verified response. So the idea is essentially to come up with baseline responses, and this is a typical response that you'll receive from a model, right? So if you prompt ChatGPT, for example, or Llama, you'll get a response of that baseline response, and then go through verification and then revise the answer based on these verifications. So those are the various steps in the pipeline. And the results that they saw with this particular technique, if you look at the table on the right, you'll see that there were three different variants or configurations that the authors used. Joint was basically utilizing a single LLM prompt to carry out both the planning stage as well as the planning being the verification planning, as well as the execution and refinement of the response. All of that was done in a single prompt. But the challenge here is that the model basically sees the kind of mistakes it made earlier as it was doing verification, planning, and execution. And because that is loaded in the same prompt, the challenge is that it tends to reference those inaccurate results that it initially came up with, and that subsequently snowballs into the refined response. So joint tip, if you look at the results, it had somewhat of a muted effect in terms of mitigating hallucination. But what they did was they looked at various different variants, two-step, for example, which separated the planning and execution into different prompts, right? So you had to run the LLM twice, and this led to, a reduction in hallucination. And lastly, they came up with a factored version, where, even after separating the planning and execution, they made sure that they did not condition the model on, the original response, right? So the model does not see the inaccuracies that it made. So that isn't part of the prompt that is fed to it, which essentially helps, not have it, not have some of those inaccuracies snowball into the final output that it generates. So factored led to some good performance. Two-step was pretty good too in certain cases. But yeah, these were the three different configurations that they experimented with. And across the board, looking at Llama 2, 70 billion, and Llama 65 billion with Wikidata and Wiki category, which is a much harder data set. They saw a good amount of mitigation of hallucination in their metrics. Now, this is a list of related papers. And like I said, I have a bigger list. So, we'll share the presentation later so you can go to that. Responsible agents. This is, like I said, a new and upcoming topic with agentic AI getting a lot of good adoption in the industry and in academia. This is still a burgeoning field. There's a whole lot of work happening, but I wanted to talk about two studies that have come up recently and they individually talk about coming up with some of these checks and balances and guardrails to ensure that we're deploying agents responsibly. But the key idea is that we want to pursue complex goals with agents, giving the LLM enough autonomy to execute actions, right? But at the end of the day, what we're seeking are trustworthy and safe actions throughout the entire life cycle of the LLM's run. So we need something that's goal-oriented, something that's accountable, and is able to decompose a goal from the user into various different individual steps. We also need to continuously monitor for risk and assess the risk at various different stages of the execution pipeline. Introduce guardrails, at both the input as well as the output. And these guardrails can be multimodal in nature as well. And then we obviously want transparency as well. So whether it's legible action logs, similar to how cloud services, for example, AWS has CloudWatch and CloudTrail that lets you see exactly what was executed as part of your particular microservice that is deployed, right? So, action logs help in understanding what kind of actions were executed. And in fact, with reasoning models, reasoning traces as well are pretty helpful in understanding, why a model took a certain course of action. And then finally, you want to make sure that you constrain the action space of the model. So, you don't let it execute all kinds of different actions. So there needs to be checks and balances at that stage as well. And, if needed, human in the loop approvals, and also specifying some default behaviors that, favor safety and lead to minimal disruption. I think those are two other areas as well. So this is a general blueprint in terms of what we typically seek when we're looking to deploy agents responsibly. Now, this is a paper that proposed a general architecture, as you'll see on the right, in terms of how to deploy agents responsibly, right? So, you'll see the user making a call to the agent as a coordinator right at the bottom, where the user feeds a goal and the agent comes back with a strategy in terms of how it's going to, address that goal, right? And the agent in this case can call a whole bunch of different other entities. It could be other tools, for example, external tools and services, could be a non-AI system, so a rule-based system, for example, and can also coordinate with a whole bunch of other different agents as well, right? So there could be a multi-agent setup as well. Multi-agent collaboration is a common theme in agents too. So, this is the general structure that they followed. But what was commendable here is that at every stage, they're enforcing a specific interface that, specifies what the input should be and what the expected output should be. So in that sense, this was an architecture that introduced some rigor, and they implemented this for a whole bunch of different, models. Meta GPT, Hugging GPT, for example, is what they utilize, and they looked at various different criteria for evaluation, right? From decomposing a goal into various different tasks. They saw an improvement there by 20%, and selecting the right agent or tool to call at any step of the pipeline, they saw an improvement of 15% there. So this was a reference architecture that this particular paper proposed. And this gets us to the last, technique for today, which is technique by OpenAI or general blueprint for deploying responsible agents by OpenAI back in 2023. And the idea was that, so this is a white paper by OpenAI cited down below, and the core idea was that they wanted to, lay out, some guidelines to deploy these agents responsibly. And what they did was essentially they suggested having task suitability evaluations, which is essentially stress testing across different deployment conditions, right? So you want to make sure that you create a whole lot of these synthetic conditions that you can eventually see in runtime, and then test your stress test your end-to-end system, which has the agent at the center, along these different conditions. They also suggested using action space constraints, which is to block some high-risk actions. Automatic monitoring, like I mentioned earlier, where you've got logs being generated from the system that you can audit, and also agent activity records, right? So this, for example, chain of thought that we see with reasoning models, dumping all of those and making sure that we're able to reference them later to dissect why a particular decision was made. And also interruptibility, right? How do you make sure that once you notice something's off with a particular run, with an agent at its center, how do you ensure a graceful shutdown, right? Where state can be then transferred back to a human, and then we can refine the next steps of the flow. Right, so these were some of the ideas that this particular white paper offered, and in terms of evaluation, they saw 80% reduction in some of the task execution errors as they carried out some of these controlled studies, and trust metrics were improved by 60% or so compared to baselines that did not implement any of these techniques. So that was responsible agents, and then I've got, like I promised earlier, I've got a list of different papers that you guys can take a look at, and we'll share a link to the slide later. So don't worry about this, but for hallucination detection, mitigation, bias detection and mitigation, and responsible agents, all of the papers that we talked about today and more papers, they're all part of this list. I've got a bunch of primers also that I've written for various different aspects. Aspects that are most pertinent to today's talk are hallucination, mitigation, RAG, and agents as well. So they're linked here if you want to go into stuff in more detail. And that brings us to the end of today's talk.